Hello guys, and welcome back to another video. Today I want to talk about the computer, how I built the computer, and how it all works. 4 years ago I started thinking about building a computer with a Z80 processor. I was impressed by the ZX Spectrum. It was the first computer I ever seen from the old days, and I was impressed by it, how it all worked with the Z80, the 48 kilobytes of RAM, etc, etc, and I wanted to build something similar. But while searching for something similar with the ZX Spectrum, I found out that the ULA, the uncommitted logic array chip, it's a proprietary chip, and it was difficult to reverse engineer and all of that. So I decided to make a standard Z80 computer with standard components, and I started searching for the manual of the Z80. I found it, I studied very well, I understood how the bus cycles were working, and then I searched for a simple Z80 tester circuit. So how to test the circuit. Somewhere over here I will put a photo of the simple Z80 circuit tester. And then I breadboarded the Z80 with a couple of additional components, such as a 555 timer for the clock, some resistors for pull-ups, and a few LEDs to show me the the status of the bus and the data bus and the address bus. And when I was ready to move up to the next level, I researched the internet how I will go about connecting RAM and ROM to the Z80. I found the basics of memory decoding and memory addressing, so I implemented that on the breadboard. Firstly, I think I added the 8 kilobytes of EEPROM, and then I added the 32 kilobytes of RAM, so it was easier to address decode and make the address decoding logic. And then I started planning how I will make the main system. I wanted it to have a keyboard input and an LCD display output. So I made this board, which consists of the Z80 processor, the 28C64 ROM, and the CY7 199 RAM chip over here, Z80 RAM. Here is a 16x2 LCD display, the classic LCD display which Arduino users typically use. Here are the status LEDs for the address bus. Here are the 8 data bits for the data bus. Here are the deep switches for programming directly into ROM. So those switches, the control panel, as I call it, it was for the first steps of the computer, so I can see the execution, I can put manually programs in, etc, etc. But after the computer was working fine, I moved up into this board. It is an Arduino EEPROM programmer I made myself using some plans on the internet with two 8-bit shift registers. Works fine. I use it all of the time to program my EEPROMs. And then I have over here 8 LEDs for the data port 0. Also over here I have some LEDs to indicate the different states of the computer. So clock, M1, read write, memory request, IO request, DMA, it's for the control panel over here, and power LED. We have here the power switch. Over here is the manually write button for the 2864. Over here we have the reset button. Over here we have the FAFA5 timer, which creates the clock for the computer. Over here we have the 74HC138, which creates the map for the whole system. This creates the chip enables and chip selects for the whole system. So over here in this board we have the, I call it the input output board because it has the speaker output is under the display. Over here we have a latch for the speaker output. Over here I've made a status register, some kind of a status register. Over here we have an external EEPROM that we can store programs and load programs from. And over here we have the joystick, a simple little joystick that I made. And over here the main, the secondary display is a 128 by 64 graphical LCD, which I'm yet to implement in the code, but it will come soon. And here, last but not least, we have the keyboard, the most difficult part of all of this construction, because you can see lots of wires. Here we have the CD4040. This chip is a 12-stage binary ripple counter, which creates the counts for these two chips. This is a 74HC151 and this is a 74HC238, which together scan the matrix of the keyboard and send it to the octal bus transceiver and then to the computer. So let me put them here. Let me see, it's all in the shot. Yes, of course. Over here, it's okay. So do not worry about the graphical LCD. It's not yet implemented fully. I don't have a driver code to work with it. I am in the middle of making a driver for it. So now we'll turn on the computer and I will show you some of the instructions that it has and some of the functionality. So turn on the computer. As you can see, I will reset again the computer. Tiny monitor, 32 kilobytes of RAM, okay, and it prints out ready with a pointing cursor and the flashing cursor which waits for input from the keyboard. So over here, as you can see, let me take the camera out. As you can see over here, the graphical LCD shows this little turret. For now it's all that it does. It doesn't do anything else. The keyboard lights up, the power button, the power LED, the power from the joystick lights up, and here you can see, let me turn off the flash, you can see all of the glory with the different LEDs. So let me position back the camera. Okay. And let me show you some of the basic functionality of the computer. So if I type help over there, right, help, as you can imagine, it helps. It shows the available commands of the computer. So pick, poke, poke plus, reset, jump, help, load, save, calc, clear ROM, dump, type, dump test, DPA test, and dump. Let's see it one more time. Help, pick, poke, poke plus, reset, jump, help, load, save, calc, clear ROM, tiny, basic, type, DPA test, and dump. So let's press reset. Oh, I did make a mistake. Reset. So let me explain some of the commands. So peek, it's used you can put an address, for example 8100 hex, and it shows you the contents of the memory address over there. So in memory location 8100 is data FF. So if I go poke, it's used for putting data into a specific memory address, poke 8100, and let me put the data 3E, let's say, and again press Ctrl X to abort the command and peek to see the memory address 8100. We can see now that the 3E that we typed, it is stored on the RAM. So what other command? Poke plus. So what poke plus does, it's the same thing that with poke, but with increment in address. So we specify a start address 8100, and it will start in the address 8100, and it will count up if when we type the data, for example 3E, it moved one address upwards. Let's type AA, it moved one address upwards, D3 00. So if we press Ctrl X is the same as escape, and press the next command, which is dump. Dump is the function that dumps, of course, a bit of the a specific address that we want for specific bytes that we want. So if I dump the address 8100, we can see the program that we stored, 3E AA D300. So press enter to move to the next 8 bytes BF, and over there is some garbage from uninitialized RAM. So we can press again Ctrl X to abort and jump to the main loop, and press jump. The jump command jumps at the start of the RAM. The start of the RAM is at 8100 hex, and when we type this command, it jumps to the start of the RAM, so it loads 8100 to the program counter and jumps, so it will execute from 8100. So let's see, and resets the computer simultaneously. So as you can see, I remember we typed, let me dump again the 8100, 3 AA D300. We'll put over here somewhere in the screen. This program loads the accumulator with the data AA and outputs it to port 0. Port 0 is, I was mentioned earlier, these 8 LEDs. So AA, let's see. 8 plus 2, A. 8 plus 2, A. So AA is displayed to this LED display. So if we change the AA and place instead of it the 55, let's say 55, we can do again poke plus 8 3E, something I did wrong. Let's abort and again poke plus 8100 3E 55 D300. Control X, press jump, and we can see that it changes according to what data we put it in. So it's now 55. So let me see the next command. Jump help said about it. Load, save, cal, clear, rom, tiny, basic, type, dpad test, and dump. So we talked about dump. Let's see the dpad test. Dpad test. So what dpad test is, I made this routine for testing the dpad. So you can see over here I have the dpad in my hand. If I press this button, it's the start button, the select button, up, down, left, right, okay. Basically this routine just shows me that the keypad works fine, and it was primarily for testing the input, the data input port. So let me control X and get out of this routine. The next commands, save and load, I've not yet implemented those. I want to implement those. So when I type a program to RAM and I type save, it will save it to this EEPROM. And when I want to load the program from this EEPROM, I will type load and the specific program of this from this EEPROM, and will load it to the RAM so we can execute it. So tiny basic, the command of the tiny basic, this is a little bit complicated. Those commands, as they are now, they are only for the monitor. I mean, the monitor, the low-level things of the computer. The tiny basic is a programming language, as you all know, and I want to have it also here so I can program in basic and not on assembly. So I want to have the monitor for the low level stuff, and then jump to the tiny basic to have a basic interpreter to write my programs there. So what else we have? Let me see again. I forgot the commands. Jump, okay, load, save. Calculator will be a calculator app, and CLR-ROM. CLR-ROM clearing EEPROM. That tells everything by itself. It clears the EEPROM, basically fills the whole 8K of the EEPROM with FF. It takes a bit. Another command is type. When this routine finishes, I will go and show you how that works. Blah blah. It takes a bit because it is whole 8K and it programs the whole 8K with FF. And the speed that I'm running this computer is not very fast. It's around 143 kilohertz. So you can see that is not pretty fast. It takes a bit. I think now, yeah, finished. Okay, let me type again help to see one more time the commands. Calculator was said, type. Okay, let me type the type. Type. Where's the Y? I lost the Y on the keyboard. Yeah, over here. Type. Type is just a simple typing program. You can type whatever you want. Doesn't store it anywhere. Doesn't write anything anywhere. Just type whatever you want. That's the type program. So Control X to abort it and get out of it. And now we'll jump to the computer and show you some of the schematics and some of the data blocks, block diagrams, and how it all works. I will show you the code, a bit of the code, not all of it, and I will talk about the software that I'm using to program my programs in. So the program that I'm using to make the assemble source. And that stuff. So let's jump into the computer next. Okay, here we are in the computer side, and now I am going to open the Eagle to show you the schematics and the block diagrams of the computer, so you can better understand how the computer works. So let me close that. Let me open the project. Here is the board preview. Haven't made it yet. So here are the main schematics. The keyboard schematic isn't ready yet, but I will explain some things over here. The main system board schematic is okay, and the I/O or the expansion board schematic is okay. Also the keypad board is okay. So firstly I want to show you some of the photos I've found and I've taken over the past of the computer building. So let me show you. This folder contains all the old images. So this is how it all started. You can see over here was the first prototype of the computer. Here having a CPU, the Z80. I think over here those three LEDs are as follows: M1 LED, I think memory request, or maybe read or write, read and write I think over here, memory request and I/O request over here. Down over here beneath all of this messy wiring is my ROM. Over here is my 32 kilobytes of RAM. Here is the memory decoding circuitry. So, and here is the address decoder for the I/O. It's separate from the memory decoding. Here is the DMA for the ROM. So if you remember, let me find a photo. Over here is the switches, the control panel. As I said, this is an early stage of the computer. So let me close that and get back to here. This was the first output stage with an 74HC574 an octal latch, I think, which output to some LEDs here, and over here is a simple input like the teapot I made, and over here is the main clock. As you can see, we moved from this messy thing to this lot of thing, where this over here. You can see a bigger breadboard over here, a lot of stuff going over here. I rewired the whole computer from scratch. Here I've made a display, a temporary display. Over here I've added the LCD, you can see here. What else? Okay, over here started all. The basic layout of the computer, the main system board, the Z80, the ROM and the RAM, the 16:2 LCD, the on-off switch and the control panel. Here you can see some of the wiring. Here is the finished project. In this stage nothing is soldered, only those little things. So my plan, firstly my plan was to use this thing as a trainer, with the expansion port over here, this port, no, here don't have it, whatever, this port for as an expansion. Okay, and I have in my mind to use it as a trainer, nothing more than a trainer, to learn a Z80 assembly code. Here you can see the Z80 processor, the what's that? Okay, yes, a time ago, when I was building the computer, I didn't have any 8K EEPROMs on hand, and I had this 8K RAM on hand, so I had to deal with it. The 555. Here you can see an early stage of the decoding logic. This was later a fail because I wanted to add some more RAM into the system. I spoke earlier with over here with the external EEPROM. If I had still this memory decoding thing, it couldn't support the extra RAM, so I added the other circuitry with the 74HC138. So here in purple we can see the power line, and in white we can see the ground lines. Here is the video, I think, but it's in Greek, so you won't understand anything. I won't show you it. Here the thing is the 74HC574, the latch for the data port 0 with the 8 LEDs. Here you can see my awful soldering. It was 1.5 years before. Yeah, it was exactly the 10 of the 3rd 2018. Messy soldering, but in the end it all worked. Yeah, trying to do some cable management. Don't look at this. Fail. Here is the computer working. I think at this point it was all working. Here is some more messy wiring. I think in brown over here we have the address bus wires. Yes, some more wiring, tedious wiring over here, and again a video of the computer. Okay, here is a more developed board. So in blue over here we have the data bus, which goes to the 574 latch for the LEDs and the LCD data inputs. In orange over here we have the data bus that spans across the RAM, the ROM, and the Z80, and of course the switches. So yes, over here some more beautiful pictures from my main board. Not really beautiful, but okay, whatever. Here I spoke earlier, I said earlier, the clock, the M1, the read, write, memory request, IO request, DMA and power LED indicators, also the reset over there, address bus over here, the manual write button for the EEPROM, the data bus button, the IO port. More wiring. What else? Some nice pictures of the Z80. Over here I started working on the keyboard. Yeah, this is the basic. This was the basic layout of the keyboard. Here were the first tests of the keyboard. You can see the logic of the keyboard over here, and as you can see here in the display, some of the numbers that correspond to these couple of buttons. As you can see, all the decoding logic from the matrix is still on the breadboard and wired directly with jumper wires to the computer. Here is a better shot. Here's a picture of the keyboard in process of being wired. Here you can see the symmetry that I like on this keyboard. It's a very neat keyboard, I think. Over here you can see also a bit of messy wiring again. This I think it's a oh, this zoom. Oh crap. Okay, this is a 74HC08. As you can see the 8 over here, this is used in combination with something else. I think I will speak about it later. I will remember it. Here is in blue the rows and in white the columns. Or no. Let me see. The white are the rows and the blue wires are the continuum of the rows, so the matrix of the keyboard. So in early stages when it was testing this. Again, some more beautiful pictures of wiring, messy as hell. Here is the finished product. After these photos, I think, yes, over here, I added the 3 LEDs over here, the power, the shift and the control LED. I lettered everything, and also I made the pseudo spacebar. And here the computer was complete. I think I have more, yes, of course. Not this one. I have the completed computer right here. Not exactly the computer as it stands right now, because as you can see, it's missing a lot of stuff, the extra EEPROM and the D-pad circuitry. Over here, not this one, I want this one. As you can read at the top of the page, it says main Z80 system boards block diagram. So over here we have the main block diagram of the system. As you can see, over here is the main clock with a 555 timer. It runs about 143 kHz and it feeds into the Z80. The Z80, the data bus and address bus, goes to directly the 8 KB of ROM and the 32 KB of RAM. And A13, A14 and A15 in combination with memory requests are used to decode which of the 2 chips are enabled on the time. So I think if A13 and A14 and A15 are low, let me think, the ROM it's enabled, and if yes, and if A15 is high and memory request is low, the chip enabled for the RAM is enabled. Over here, the 16x2 LCD gets its 8 data bits, the A0 to select which register it is, the command or character register, and gets the right signal. The chip enabled screen comes from this 74HC138 chip, which, as I said, controls all the chip selects of the I/O. So from 00 hex to C0 hex, 20 hex apart, so it is 00 hex, 20 hex, 40 hex, 60 hex, etc. Here you have the DMA control. The DMA control is the control switches with the LEDs and all that stuff. And here we have the 74HC574 for the 8-bit display, the discrete LED display. And that's all for the main system board. So let me get out of the zoom and get back. So here is the Z80 I/O board, the expansion board. Here we have at the top of the board the 74HC574 LUTs, which it's on port A0 hex. This is a sound port which the 8 bits are split in half and go to two chips, the 4066 bilateral switches that control a 555 piano circuit. I will show you it later in the schematics, and control the sound speaker. Here we have the RAM, the other not the RAM, the other ROM, the expansion EEPROM. So it gets the 8 data bits, 13 address lines, read, write, and a chip enable. Also the 128 by 64 graphics LCD gets the same A0 to control in which register we are. So if A0 is 0, we are in character mode, and if A0 is in 0, we are in command mode, and if A0 is 1, we are in character control command mode. Damn. It gets a write signal, a chip enable signal, and also 8 data bits. So here we have the keypad circuitry, which goes into 74HC574 LUTs, and these D0 to D7 goes in to decode the correct key that's pressed, and also here we have a debounce and delay circuitry. And here the most interesting part is the circuitry from the circuit board, from the keyboard board. So as you can see here, we have a 60 it's divided by 64 counter, binary counter. I used the cheap the 12-stage binary counter. We have a 50 kHz gated oscillator. We have a binary to 1 of 8 decoder, basically 74HC151. Here we have 1 of 8 data selector, basically 74HC. No, I swapped them around. Here we have a 74HC 238, and here we have a 74HC 151. This spits out 8 signals one at a time. Basically it goes 1 0 0 0 0 0 1 1 1, we can, and etc etc etc, goes bloop 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 bloop. And this 8 by 8 keyboard matrix, when the button is pressed, basically makes a connection, let's say from this pin to this pin, and this decodes it to over here and sends it then to the computer by this port. The key press is the signal that tells to the computer that, hey, I have a character from the keyboard, let's read it. So the debounce delay, as we spoke earlier, the circuitry with a 555 timer, and here is the circuitry to control which special character shift on control. So those were the photos, and those are some more photos of the computer. This is a schematic by John Chiambikas in the YouTube. You can find it. It's a simple Z80 computer that I based my first experiments on. And that was all from the block diagram. So let me now jump into the schematics. Okay, here we are on the schematic side of things. And here starts the difficult part, explaining the schematics. Over here on the top we have the classic power jack, the power on slide switch, the power LED with the complementary decoupling capacitor, one for each chip. Here we have the capacitor, the 555 timer oscillator. Place a capacitor negative to first pin, positive to third pin, capacitor range 1 nanofarad to 100 microfarad. For normal operation, use 1 nanofarad. For debug, use high value slow down the computer. So what I mean here, as you can as you saw in the computer over here, where it is over here, you can see over here that the capacitor is not soldered in on a 3-pin socket. So this 3-pin socket, you can, yeah, there it is. It's a 3-pin socket. You can need to change the capacitors to slow down the computer or make it faster. So let's move on. Here is the classic 555 the Z80 processor with all the pull-up resistors and stuff. Here is the EEPROM, here is the RAM, here is all the control panel things, here are the control status LEDs, here is the LCD, here is the 574 for the 8 discrete LEDs. Here's the 74HC138 with which it's, as we said, the main suspect for the chip select for all of the computer, 00 hex, 20 hex, 40 hex, 60 hex, 80 hex, 80 hex, and 0 hex. So this is the 74HC138 that controls the chip enables for the ROM, RAM, and the external storage. As you can see here that ROM chips enable, storage chip enable, and RAM chip enable. So what else? From this schematic, I don't think I'm left anything. Here I think, here is the manual right button, here is the reset and power on reset circuitry. So let's move on to the expansion board. Okay, here is a big one. Here is the circuitry that makes the sound. So basically I've copied from the internet. Let me find it. Timer piano. Okay, found it. Let me find the correct picture. It's over here. So this picture, let me make it bigger. Nah, not really bigger. So this picture, it's the same as the circuitry over here, but instead of the switches, I have those 4066 bilateral switches controlled by the 574 LUTs. So instead of controlling each button manually with a hand, we can control it through the data bus. So we can make sound through the data bus. Over here is a simple status register thing that I made. Basically we got an inverter coming from 60 hex. Basically the computer reads at 60 hex and it reads the first 2 bytes of the 8 bytes, 2 bits of the 8 bits of 1 byte. So, and sees which bit is on. If there is the bit 0 off, means that we have a character from the keyboard. If it's on, we don't have anything. And if the second bit is off, means that we have a pressed key from the D-pad. Here is the external EEPROM. Here is the graphical LCD with the complementary parts, the reset button and stuff like that. And here is the D-pad circuitry. I am missing something over here. Yes, I am missing this part. I will copy it. This is the debounce delay circuitry. I will talk about a bit. Here we have the input from the D-pad. It goes through a diode matrix just to send a signal to the status register. And here we have the 574 um, to store the data from the D-pad and send it to the computer. And here it's the keyboard circuit diagram, but it's not complete. I will complete it. Basically, we have the 4040, as I said, which creates the binary count over here, and latches the count on these two chips that together scan the matrix. Here we have the gated clock. How the gated clock works: basically this 5555 timer speeds out the clock in one of the gates of the inputs of the gate of the AND gate, and this chip, when it's powered on, it spits out an active low signal over here. But if a key is pressed and we detect a signal over here, then this active low, no, I'm sorry, it's active high. So if it's powered up, this output, number 6 output, it's high. So continuous clock over here and a high here gives a high over here. So the clock runs here. If a button is pressed, it detects that, and this output goes low, this output goes high, and this output goes low. So a continuous clock here and the low here means that we have a low here. So the clock stops, and it stops at the exact binary value of the key that we pressed. So this binary value over here from this 6 4 over here and the other 3 signals over here will go into this octal bus transceiver and then into the computer. And last but not least, we have over here the D-pad circuitry. That's not that difficult to explain. Basically, we have 7 switches that are hardwired in the connector and went and go into here to the LUTs. And that's all from the schematic side of things. I will provide the download link when I'm all finished with the schematics down below, so you can see them, you can change them, you can understand more better with the block diagrams and some photos. And now I will jump to the code part of things a bit later. So we are here over on the code side. Let me open the Z80 simulator. Okay. So this is the code, the main code. So the Z80 simulator IDE, it's a very nice application, a very nice program that both simulates and lets you create code for the Z80. I will put a link definitely in the description of it. So here let's see the code. Over here we start with tiny monitor for Z80 SBC, main map, ROM located at 0000 hex through 1000 FFF hex, empty space, the ROM socket that we said the expansion ROM is located from 1 FFF hex through 7 FFF hex, and the RAM is located at the 8100 hex through FFFF hex. The stamp pointer is located at 8088 FF hex. Over here is the I/O ports. Over here is some nodes. Over here we set telling the CPU that is the start of the RAM is at 000 hex. To put the code, we clear the character count and line count. We are initializing the displays in the sound. Firstly the 16x2, then the A128x64, and then the sound port. Then we are displaying the startup message logo and playing a tune. The logo is a chart that we said. The start message is a tiny monitor, 32 kilobytes, okay. And the tune is a startup tune. Here are all the internal function, display character, string loop, new line, backspace, first line, second line, CLS, clear screen, keyboard ready, get character, make a hex, which basically makes hex from the ASCII, makes uppercase, get string, etc, etc. As you can see, all the code is very well commented, so you will not have any problem. Here is the start of the main program. We load the A with 00, out sound A, we turn off the sound port, load the HL with the start text, the ready and the pointing cursor, and call string loop. Then we have here the command loops, pick, poke plus, reset, jump, help, calculator up, routine that fills the ROM with FFF, jumps to tiny basic, just what you type to the keyboard split the screen, jumps to the t-pad test, jumps to the save routine, dumps the contents of a specific memory address, and here it's printing invalid message. The tiny basic, the jump command, the reset command, the pick command, the poke command, the poke plus command with auto increment, the help command which displays the available commands, the clear ROM routine that clears the ROM, the dump, it dumps the specific routine, the specific start address 8 bytes at a time. What else? Here is a d-pad routine test, a long routine. Here is the save routine, just jumps again to the command loop. Also the calculator jumps the command loop. Type, just here it's a small routine for the type program. Over here we have the bitmap loop, which displays the little turret over on the graphical LCD. Over here we have the sound loop that loops and makes the sound. Over here we have some strings, the tiny monitor, 32 kilobytes of RAM, the ready, splash screen. Here we have the strings for the which they will be displayed on the screen. Here we have the commands available: pick, poke, plus, jump, reset, help, load, save, calculator, clear ROM, tiny basic, type, d-pad test, and jump. Here are the command strings. Here is the array for the bitmap, and here it will start I will start over here the tiny basic program at 800 hex. So if we file tools assemble and load, we can see that the whole monitor programs cancel. Okay, we can see that the whole program is about a 2K, I believe. Let me recompile it. Tools assemble and load. Yes, 1.46 kilobytes. And now, if you remember the ports that we said, here we have the 20 hex port, the 80 hex port, the 21 hex port. This is the data of the 16x2 LCD, the character command mode, and this is the data mode. This is the character mode on the graphical LCD, and this is the sound output. So if we go to tools and breakpoint manager, here it allows you to set breakpoint managers and trace the program. Tools, simulation log viewer. Here it's logs as the simulator goes. So if we go rate ultimate and start, you can see over here it prints out tiny monitor, 32 kilobytes of RAM. Okay, if I clear it, here now it will play the loop of the sound. Oh god, I forgot to Yes, I forgot to go here and make the sound loop a bit smaller because it is very slow here on the computer to load. I think here the computer runs something like 50 kilohertz or even slower. Tools, breakpoint manager, and the port clear over here. So tools, simulation rate, simulation start. Here you can see the execution of the program. So here we can see the sound port when it makes a sound, and here is Z80, and here asks us for an input. This input, the computer will receive this input from the status register. So as we said, if the first bit of the status register is 0, then we have a character waiting. So let's test it. If we type 01, okay, wrong, why, semicolon. If we type 01, it will return into the same 60 hex port. Enter. Yeah, you see. If we type 00, it will continue in the 40 hex port, which is the data input port from the keyboard, and it will wait for a text, a character, let's say 48. I think it's H. Okay. Let me open a Google Chrome and see the ASCII table, so we can type help. Let's say help. So the E is 45, so let's type again 00. Yeah, 45. 00. L is 4C. 00. P is 50. So you can see here that we typed help, and if I type again 00 and 02, which is the enter command, then displays the available commands: pick, poke, poke plus, reset, jump, help. So it will be there for a long time because again I've put a lot of delay between those screen splashes of the commands. So I will have down in the descriptions my website, which you can go on my website, and it will have download links for the code, the schematics, the block diagrams, and also on the web page I will explain more. I will have a blog type of thing which I will explain more for the computer. I will have some more pictures. Yeah, I will have a lot of things, downloadable links over there. I will linking down below the Z80 simulator IDE, a very friendly user and beginner friendly program, which allows you to easily create Z80 assembly programs, as you can see. And also if you like the video, please give it a big thumbs up, because it is the first video I'm doing that is so long and it's explaining so much things in one shot, so it will help me a lot. And if you are interested in these sort of things, please subscribe to my channel. More things are coming, and also I think if the time allows it, I will start a series on how to build a Z80 computer from scratch. but with not that things that I've built this one with some serial communications, and I think 8 kilobytes of EEPROM and 32 kilobytes of RAM. And also I will make a small monitor program, nothing like basic or anything like that, and it will use the 68B50 Asia asynchronous communications chip, so it will be interesting. As I said, that's all. Thank you very much for watching. If you stayed until now, thank you, big thank you. Like, share, subscribe if you liked it. That's all. Until the next time, I hope you are okay, and I will see you then. Bye bye.